Hi everyone, my name's Alex. I'm an engineer and my passion is with design, development and prototype production of all sorts of engineering solutions. Welcome to the first episode of this 4-part video series on welding distortion. In this episode you'll get an overview of the upcoming experiments and we'll take a look at the key principles of welding distortion. So let's take a look. Sorry guys, but I must give a verbal introduction to the subject first, since it's not an easy matter. But we'll also do some interesting experiments in this episode. Every welder has encountered it, but no one likes it: welding distortion. Welding distortion can be severe enough to lead to complete rejection of workpieces or even whole designs, if these must have low tolerances in shape and/or size. Until now, no practical welding technique has been invented which brings forth distortion-free workpieces. And this includes the recent additive manufacturing techniques, since they are closely related to classical deposition welding. However, there are methods which allow to influence and reduce welding distortion. Also, we can straighten welding distortion via the smart application of local heat, known as flame straightening. Both of these subjects are treated in the individual episodes of this video series. During welding of a workpiece, countless processes take place in it. Most of them we cannot perceive with our 5 senses, such as microstructural transformations of the material or the formation of internal and residual stresses. This is probably the reason why welding distortion is so difficult to understand without the aid of particular experiments. Part of the experiments shown in this video series I also exercise in the day course Welding Distortion as a part of the practical course Material Mechanics, which I teach at Professor Ewald Werner's Institute at Technische Universität München. During my professional lifetime I could find only limited information of practical use on the subject of welding distortion. Also, I failed to find a figurative explanation of the driving mechanism behind welding distortion, even though I tried to have an overview of the relevant literature. A figurative understanding of this mechanism, however, is quite important for successful design and fabrication of welded components with minimum distortion. This is why I decided to try my best sharing some findings via this video series. But don't worry, the contents are tailored for practical people like, I guess, you and myself. Welding distortion is thermally induced and after cooling residual distortion of a workpiece. It is driven by a few individual mechanisms which we will distinguish according to their impact as primary and secondary. The primary mechanism of welding distortion is subject of this video series. Secondary mechanisms are, for example, opening and closing of gaps during welding, microstructural transformation or magnetostriction. The last two, however, in most practical cases play an insignificant role. The primary mechanism of welding distortion is found more or less pronounced in all ductile, that is, formable metals. In these materials, qualitatively we always find the same behavior of distortion. We encounter it not only during welding, but also during quenching with heat treatments, for example hardening or precipitation hardening, or we find it in additive manufacturing. The experiments in this video series we will conduct on steel samples, since steel is the most common material processed by welding. Furthermore, steel allows for rough visual judgment of temperature via radiant heat colors or tempering colors, also known as discoloration, unlike, for example, aluminum does. The results of the experiments, however, are qualitatively similar when using other common metals. The primary mechanism of welding distortion is driven by unequal temperatures in the workpiece. These cause unequal thermal expansion of it, which is balanced by local elastic strain, which in turn causes local stress. As soon as the local stresses reach a certain absolute value, that is the yield strength of the material, they give rise to local plastic, that is residual, deformation of the workpiece. The combined local residual deformations are the major part of our workpiece's welding distortion. The minor part of welding distortion is caused by residual stresses, which the workpiece is subjected to after cooling. The latter part may be only a fraction of the total distortion, but it can lead to additional springing back distortion with subsequent machining or heat treatments of the workpiece. But even if the welded component is put into operation right after welding, residual stresses pose a certain problem. They add to the stresses which the component encounters due to operation. Consequently, they may reduce the strength of the component. That is why in the practical world, in most cases such welded components are oversized and strictly required to possess pronounced material ductility and toughness. The latter potentially allow for reduction of high residual stresses in case of the first maximum load or overload. The primary mechanism of welding distortion takes place while the material is solid, during local heating or cooling. Consequently, we can study the primary mechanism without local melting. In other words, there is no need to weld in order to study distortion as we encounter with welding. This is, for example, the case during flame straightening, where we turn the tables. Here we smartly apply local heat to create on-purpose distortion in order to counteract welding distortion. As you'll see from the following, the primary mechanism of welding distortion is controlled by temperature difference between workpiece and heated zone, by workpiece flexibility, and by heated zone size. Furthermore, to control distortion, the heated zone can be influenced with welding sequence and weld symmetry. As already mentioned, a secondary mechanism of distortion is the opening and closing of gaps. We control this particularly with weld preparation, clamping, and with tack welding. This is a quite straightforward geometrical problem and therefore only discussed in the last episode. This video series should assist in gaining an understanding of the primary mechanism of welding distortion. Of course, this will not allow us to forecast distortion quantitatively, but rather qualitatively. This understanding should also enable one to plan tack and welding sequences that result in lower distortion than using no particular sequence. Also, it is crucial for flame straightening, where key to success is to smartly decide about location and size of the heated spots. Distortion of welded components can be hard to forecast, in some cases even qualitatively. But let's not start where it gets complicated, rather let's first study the primary mechanism of welding distortion with the simplest experiment possible, which is the single heated spot. Weld beads can be understood as an array of heated spots. Of course, in a weld bead they do interfere with each other and change the situation a bit. However, the mechanism in weld beads is qualitatively the same as with the single heated spot. Let us begin with studying the effects of the single heated spot on this piece of 3 mm mild steel sheet metal. First, we want to place a heated spot somewhere on the inside of the sheet where we can measure the thickness with the micrometer. If you want to do this experiment for yourself and have a micrometer like this, keep in mind that the throat depth is limited. So in this case we could place a heated spot approximately here. But for the experiment at hand, I will be using this thickness gauge here, which allows us to take a spot right in the center. So let's take this spot right here. Next we measure the initial thickness of our spot, which here amounts to, it's an odd thickness, and it amounts to 3.12 millimeters. Now I'll heat the marked spot with the oxyacetylene torch, let's say to an orange red. The oxyacetylene torch is my choice for this experiment because with it we have good control of not melting the material, which is required for the subsequent measurement. You can use the tick torch instead, but make sure that you do not melt the sample surface. The sheet under the sample is just for protection of the table. In the meantime, the sample has entirely cooled, so let's measure the spot's thickness again. It now amounts to 3.22 millimeters. Okay, so what we observe here is that the heated spot thickened. Now, with the measurements we've taken and our initial thickness being 3.12 millimeters and our final thickness being 3.22 millimeters, we can compute the thickness strain. And the thickness strain equals 3.2%. Now, the interesting question about this thickening here is this deformation of an elastic nature? Like if we compress this foam here, which springs back as soon as we take away the stress? Or is it rather a plastic deformation, like if we compress this putty here, which remains deformed if we take away the stress? This is a crucial question because our ductile metals, which we usually weld, can do both. We may answer this problem with the aid of the thickness strain which we computed earlier. What we know from ductile metals in general is that they can take somewhere between 0.1% and 1% of elastic strain, the strain, until they start to deform plastically, like the putty. With our thickness strain being 3.2%, consequently we know that the major part of the deformation here is plastic. There is surely some elastic deformation due to residual stresses present too, but this is most likely only a little part of the thickening. Now let's measure the thickness a little away from the heated spot center. Again, as we measure the heated spot center, we have the 3.22 millimeters, and let's go to the area where the discoloration begins, like here. And here you already see that we have the initial thickness of the sheet again, 3.12 millimeters. So what we learn from this is that the thickening is almost limited to the area which was red hot. But why does this area thicken anyway? Well, as we heat the spot with the torch, it wants to expand equally in all directions. It can expand quite freely in thickness direction because nothing much constrains it there. But the expansion in the sheet's plane is very much hindered by the cold surrounding rest of the sheet. This in turn is experienced by the heated spot as radial compression. As temperature rises, the compression stresses rise and sooner or later exceed what the heated spot can take. Then it begins to behave like a very strong putty and flows in the direction which is the least stressed. And here, this is the thickness direction. A student of mine proposed a very good interpretation of this behavior when he said that it is like baking a cake. The cake rises in the oven because the cake tin constrains it radially. You may laugh, but this is pretty similar to what we observe here. This next experiment should highlight the rising cake explanation and give us an idea of the residual stresses that develop due to the heated spot. For this we will heat the central spot of this 3 mm mild steel sample here, just like before. But other than before, the spot we will heat is actually a plug which very exactly fits into this hole in the sheet. For this experiment to work correctly, plug and hole must have very good surface quality and be burr and chamfer free. And if you wonder how to make such parts burr and chamfer free, you can, for example, gang 4 or 5 blanks with super glue together between these two arbors here. Take this one in the chuck or in the collet in the lathe, put the tailstock here and turn them to dimension. Then you must break them apart and discard the outer ones. The inner ones can be kept for this experiment. They should have a sharp and exact corner. Same works for the sheet. You can gang 4 or 5 of them together with super glue, ream them to dimension and then break them apart and discard the outer ones and keep the inner ones. Before we heat the assembly though, we must note the plug's dimension. Thickness is 2.98 millimeters and diameter is 10.01 millimeter. And the same for the sheet. Thickness is 2.98 millimeters and the hole diameter should be fairly close to the plug. So that's 10.02 millimeters. As I assemble this thing, pay close attention to how exactly the plug fits the hole. There is barely enough clearance to assemble them without force, just right for the experiment. In the meantime, the assembly has now entirely cooled, and as you can see, the plug's diameter is now notably less. We can also see this if we take a closer look at plug and hole interface. And here you can nicely see the gap. But let's measure this. The plug's thickness now, it formerly was 2.98 and it's now 3.12 millimeters. 3.09 millimeters. So that's approximately 1/10 of a millimeter thickening. And the diameter formerly was 10.01 millimeter and it's now 9.9 millimeters. So the diameter decreased. The hole, on the other hand, Let me check the thickness close to the hole. It was 2.98, it's 2.99, so that almost didn't change. And the hole diameter was 10.02 and now is entirely unchanged. So the deformation of the plug proves the plastic deformations which we discussed before. But by comparing the two previous experiments, we can learn something about the elastic deformations due to residual stresses too. The two experiments are mechanically similar up to the moment when cooling begins. Then they start to differ because of a gap that develops between plug and sheet. Here, instead of a gap, radial stresses develop, where hot and cold zones interface. In other words, the heated spot gradually experiences radial tension, whereas the hole experiences radial stresses which try to close it. So you might say the heated spot causes a local pinching of the sheet. This is the most essential aspect about welding distortion, which we must keep in mind. But now let's explore the heated spot thickening a little more. First, let's place the heated spot closer to the edge, say here for example. Initial thickness is 3.12 or 3.13 millimeters, just as with the first one. I'll try to heat this one to the same temperature as the first one, or at least as close as I can get it by radiant heat color. Thickness after cooling is .16 millimeters, which gives a thickness strain of approximately 1%. So it's notably less than what we got with the first one. But why do we find less thickening here? Right, it is because the thermal expansion of the heated spot wasn't constrained much in plane of the sheet, since it is located so close to the edge. This is the second essential observation about welding distortion. Since thickening correlates with distortion, we keep in mind that less constraining of the heated spot's expansion gives less distortion. Next, let's do the same as in the very first case. Place a heated spot in the center of this sample here. Except that this time we evenly preheat the sheet to, well, let's say a blue tempering color. Initial thickness here is 2.98 millimeters, and after preheating I'll try to heat the heated spot to the same orange radiant heat color as the first one. thickness after cooling is 3.02 millimeters, which gives a thickness strain of approximately 1.3%. This one is also notably less than what we got with the first spot. But why do we have less thickening in this case too? Since the surrounding sheet was preheated, the cake tin was expanded too, which gives less constraining of the heated spot. This is the third essential observation, and we keep in mind that distortion is not controlled by absolute temperature, but rather by temperature difference in the workpiece. Obviously, the lower the temperature difference, the less distortion develops. Now, finally, let's heat the first spot again and see what happens. Local thickness here after the first heat is 3.22 millimeters. Skip the head in time and let the sample cool, and the thickness now after the second heat is 3.25 millimeters. In the first run we've gained a thickening of 1/10 of a millimeter, and now we've gained approximately 1/3 of that. Of course that's less, but still the spot thickened even more. You can try for yourself. Thickening will continue with even consecutive heats up to a certain situation. Before that, probably surface scaling will inhibit a reliable thickness measurement, but you have to try for yourself. This is the fourth and final essential observation on welding distortion of this episode. You can try these experiments for yourself if you like, with steel or other metals. Also, you can vary the sheet thickness. Too thick sheets though are problematic to heat through, while too thin sheets tend to buckle. Nonetheless, if you compute the thickening in percent like we did earlier, you should find similar numbers and behavior as we got before. Higher percentages are typical for distortion susceptible materials and vice versa. But keep in mind that the heating temperature influences the result. Well, so far for episode 1 of this video series. In the next episode we'll take a look at the residual stresses which develop in our workpieces and discuss why they develop, even though we'd very much like to avoid them. Thank you very much for your interest in this video. I appreciate your time. All the best for your welding project, and thank you.